Hi, everybody. Welcome to this, one of our very first sessions as part of our Symposium 2020. My name is Diana Sinton. I'm the Executive Director for the University Consortium for Geographic Information Science. We have an exciting lineup of activities this week, beginning in just another minute now with a series of presentations by individuals who are part of our research committee. As a reminder, in this GoToWebinar interface, your own microphones are muted by default in this. If you have a question, please type a question into the question space, which can be activated by clicking the little question mark icon. And if you need some other type of attention, you can raise your hand. And I can try to do some troubleshooting for you. But this webinar interface is really more designed for one-way communication than two. So please use the question space and we will be monitoring that. And I see people are still signing in right now, but for the sake of time in our schedule, I think we'll get started. I want to thank very much Dr. Shilung Shah, the research chair of our committee, from University of Tennessee, Knoxville. And I would like to introduce our first speaker for today. That would be Dr. Yingji Hu from University at Buffalo. Yingji, it's all yours.
Okay. Hello, everyone. So the title of my presentation is NeuroTPR, a neural net toponym recognition model for extracting locations from social media messages. So social media platforms have been increasingly used by people in natural disasters to request for help and share information. And here are a few tweets from the 2017 Hurricane Harvey. For example, one tweet wrote, 12-year-old boy needs rescued, and then provided the door number and the street name. Another tweet wrote, anyone with a boat in the Maryland area, a pregnant lady named Lisa is stranded near this intersection of these two roads. Or another tweet wrote, rescue needed, and provided a detailed address near the boat rescue. There are 3 people and 2 elderly not steady in her feet. And of course, these 3 tweets cannot represent all of the tweets sent out during Hurricane Harvey or a natural disaster, but they do demonstrate the urgency of some of these rescue requests. And effectively extracting locations described in these social media messages can help first responders reach the people in need. And when we are talking about locations with social media, there are 2 types of locations that we often talk about. So one is the geotagged locations that has been used in many of our GIS science research. Basically, we have GPS locations of the Twitter user, and when a Twitter user sends out a tweet, the location of the user was attached to such a tweet. And this information is available in the metadata. So if we use the API of Twitter to retrieve some tweets, we will be able to directly get the latitude and the longitude. And the previous research shows about 1% of the total tweets have geotags. In June 2019, Twitter removed their precise geotagging feature, and our recent research shows that the percentage of geotagged tweets is further decreasing. So the second type of location is the locations described in the content of a tweet. And this shows where the tweet was talking about. They are not directly available, but need to be extracted usually from the content of the tweet using some natural language processing methods. And the previous research has shown over 10% of the total tweets contain some location references. So we are going to focus on the second type, and which are related to the locations in these rescue tweets. And if we are going to talking about extracting locations from social media messages, or more generally from from texts. This is related to the research topic of geoparsing, namely trying to recognizing and geolocating locations from natural language texts. And two steps are typically involved in geoparsing: toponym recognition and toponym resolution. So for the input of a geoparsing software called a geoparser, we have some input text, which can be social media messages, which can also be just some general texts. And then it goes through this toponym recognition step, which recognizes the location mentions from the text, and the toponym resolution step, which locates these location mentions on a map. So eventually we will be able to get the locations based on the descriptions on a map. And this is the focus of our work, the first step, toponym recognition. So in existing research, typically off-the-shelf named entity recognition tools such as Stanford NER and also Spacey NER are used for toponym recognition. And what this NER tools does is that they take a piece of text as the input and outputs different types of named entities, such as persons, organizations, and locations. So for example, we may have a sentence like this, right? So donations to the Red Cross have provided help for people in Texas impacted by Hurricane Harvey. And an NER tool will be able to recognize that Red Cross refers to an organization, Texas is a location, and Hurricane Harvey refers to an event. So intuitively, a very simple approach we can do in using an NER tool for toponym recognition is that, well, we simply keep locations in the output, and then we just ignore the other types of entities recognized. And indeed, this was what is typically done in existing research, and there's quite some advantages of doing so. We don't need to develop our own toponym recognition model from scratch. It's low cost. We don't need to train our own machine learning model. We don't need to spend human and time resources on such work. And these NER tools, they indeed have good performance on well-formatted text, such as news articles. However, existing NER tools have limited performance on user-generated text, such as the content of social media messages, which often have misspellings. So one may, for example, when typing the word California, may miss the letter I or type a different letter. There can also be inconsistent upper and lower cases. For example, one person may write, there is a huge fire near Camino and Springbrook Road. There can also be language abbreviations. So one may use PPL to represent people, may use PLS to represent please and at symbol, especially in tweets when there is a limitation on the length. And also there can be informal sentence structures. This user-generated text may not follow the strict subject, predicate, and object components, but may miss certain parts. So in this work, we propose NeuroTPR, which is a neural net toponym recognition model for extracting locations from social media messages. And here is the general architecture of NeuroTPR. And it is based on a bidirectional long short-term memory architecture with 7 layers. So at the bottom, we have the input of this model, which are the tokens or the words of the tweets. And these words, they will go through the 7 layers, and then eventually the output of the model will determine which words they are part of a location such as in this case, Solomon Road will be considered as a location here, and which words are not, such as is flooded, they will be considered as not location here. So let's look at this model in more detail. So for layer 1 and layer 2, we use 2 layers of character embeddings to represent each individual word. So basically, each individual word here is represented as a sequence of characters modeled by a bidirectional LSTM model. So for example, the word Solomon will be modeled as a sequence of letters like S, O, L, O, M, O, N. And the advantage of doing so is that using these character embeddings can help us handle misspellings in tweets. So if a word misspells one letter or misses one letter, the semantics or the words, the meaning of the word is still largely captured. In addition, we also use 2 layers of caseless and case-sensitive embeddings here to help us handle the irregular upper and lower cases in user-generated text. In layer 3, we use pre-trained word embedding GLOVE, and which is pre-trained on about 2 billion tweets. And the advantage of using this tweet-based word embedding is that they can help capture the semantics of the irregular words such as PPL, such as PLS, that are often used in tweets. In layer 4, we add 2 linguistic features. One is the part of speech, POS, and what this feature does is that it informs the model which word is which type. So for example, whether a word is a noun or a verb or is a preposition. In addition, we also use ELMO, which is a deep contextualized word embedding. And what it does is that it captures the changes of the semantics of a meaning based on the context it is used. So we all know some words, they can change their meaning depending on the context, right? So the word bank used in the context of a river compared with used in the context of a financial institute. And finally, it goes through this bidirectional LSTM layers, and the forward LSTM captures the context of the word from its left side, and then the back LSTM captures from the right side. The result is connected into a fully connected output layer, and then finally we have the conditional random field layer, which determines the types of each individual word. So we have the model, but a challenge is that how do we train it? And obtaining a sufficient amount of labeled training data is often a bottleneck for training machine learning models. In this work, we use 2 data sets for training NeuroTPR. One is 599 human annotated tweets from a previous competition based on Twitter data. It's called WNUT 2017. So this is a real data set with tweets, but as you can see, it is quite small. So we also use a second data set, which is automatically generated using a proposed workflow, and they are generated from Wikipedia articles. So the core idea of this workflow is to generate the training data from using the first paragraphs of Wikipedia articles. As you know, in many Wikipedia articles, they will provide hyperlinks on certain entities or concepts that are in the text, right? So in this case, we have Canal, we also have New York here. So what we can do is that we can just keep those hyperlinks that point to location-related Wikipedia pages, and then we generate labeled training data from that. So for this part, we did quite some experiments, and initially we thought we could just directly use geotagged Wikipedia articles, but it turns out geotagged Wikipedia articles, they do not always refer to locations. So eventually we used the template provided by Wikipedia and found out it's quite useful for distinguish locations from the rest annotations. So this is getting into more technical detail. If you are interested, let me know. I'll be happy to share more details here. And then we divide a paragraph into short sentences to simulate the length of these tweets. And then we also propose a strategy of random flipping to simulate some misspellings in the text. So a word such as Solomon may become, for example, SOLE. So the letter O may be changed to E randomly, and then we may also miss a letter like this. So we have the model, we have the training data, and now we can do some experiments to test our model. We use 3 test data sets, but particularly we are going to focus on one, which is about Hurricane Harvey. This data set has over 7 million tweets retrieved during Harvey and collected by the libraries of the University of North Texas. We extracted 1,000 tweets, first using a regular expression, focusing on locations, and then did some random selection. Eventually, we manually annotate this 1,000 tweets and then use them as the ground truth. So I also provide the link of this Hurricane Harvey dataset here, and you can check it out. The evaluation criteria we used are precision, recall, and F-score, which are typically used in geoparsing research. We also compare our model with a number of baseline models, and we use the existing NER tools that are typically used as a toponym recognition model in geoparsers, so such as Stanford NER. And Stanford NER also provide a caseless version, which can handle you capitalize the text. So we also include this version here, and also spacing NER. We also use 2 deep learning models as our baselines. One is a basic BiSTM CRF proposed by NAMPO, and another is DMNLP, which is the winner model in a recent geoparsing competition. However, using these existing NER models for toponym recognition is not that straightforward. For example, if we use Stanford NER, it outputs 3 types of entities, which are location, organization, and person. Intuitively, we can just use the location as our in the output, but doing so will miss schools and churches, which are often used as shelters, because schools and churches, according to Stanford NER, they are considered as organizations. So alternatively, we can use both location and organization, but then that will also include false positives. Similar situation happens to spacing NER. So spacing NER also output a category called location, and if we use location only, it will only recognize natural geographic features such as rivers and mountains. And if we use all geographic related entities such as facility, organization, geopolitical entities, then there will also be false positives. So eventually we tested different versions of these models, and so in total we have 9 baseline models. So we have another version of the model, which basically we only focus on the location of the output. So a broader version contains, for example, location and organization for Stanford NER. We also retrain the Stanford NER using our own training data. Because we have 2 different data sets, 2 different training data sets, and the second training data set can be in different sizes because it is automatically generated. So we can actually train neural TPR in many different ways. So here we test 8 different training strategies, including just use the real Twitter data set, WNUT, or the automatically generated training data with different sizes of Wikipedia articles, or with the random flipping strategy, or with a combination. Eventually, we found that firstly, more training data is not always better, especially when the training data contain noise. And so this is the case, especially if you look at the performance of the model trained using 3,000 Wikipedia articles compared with using 5,000 Wikipedia articles, the performance actually decreased. And we looked into the results, and one major reason is that the annotations generated from Wikipedia articles actually contain noise, because Wikipedia articles, they do not annotate all of the entities, and as you can see in many of these Wikipedia articles, so they actually include some of this noise in the training data, and training our model with more of this noise related training data, they can actually decrease the performance of the model. And we found that a combination of a moderate size generated training data with the real Twitter dataset works the best, which achieves the best performance here. And we also compare our neural TPR model with the baseline models on Hurricane Harvey tweets. And we found that Stanford NER actually achieves the highest precision. And this shows the effectiveness of this very classic model. But as you can see, its recall is quite low. It's only about 0.4, which means over 60% of the valid locations in these tweets they are actually missed. And we looked into the result. We found that most of the toponyms recognized by Stanford NER, they are city names, such as Houston, or such as nearby city names like Pasadena, like Deer Park. And these city names, they have limited value from a disaster rescue perspective because of their coarse spatial resolution. The highest recall was achieved by DMNLP, and overall our neural TPR model achieves the most balanced performance in terms of F1 score. And we also compare our neural TPR model with the baseline models on 2 additional data sets, because our previous research has found that the same geoparser can have different performances if different test data sets are used. So we use one Twitter dataset, which was developed by the GeoVista Center from Penn State University. And we use another dataset, which was developed by the STQ lab from UCSB. Eventually, we still found that neural TPR still achieved overall the best performance. So conclusions, in this work, we proposed neural TPR, a neural net toponym recognition model for extracting locations from social media messages. This model is based on a basic BiOSTM architecture and with several special layers to handle language irregularities in tweets. And we also propose a workflow for automatically generating labeled training data from Wikipedia articles. And neural TPR is the first part. It is a toponym recognition model and can be further combined with a toponym resolution model to perform a complete geoparser. So that is all. The source code of this work is also available on GitHub. So please feel free to try it out. And this work is also part of the outcome of our GeoAI research initiative of UCGIS. So that is all. Thank you very much. So so maybe we can take some. Maybe we can take one question here. So any question here?
And as a reminder, if you have any question, please feel free to type it into the question panel, which you can open up by clicking on the question mark icon on your webinar interface.
Okay, so maybe meanwhile, because of the time, maybe we can also get Zhe prepared for her presentation. So Zhe, I will switch the presentation mode to you.
Thank you, Yingjie.
Okay, great. Yeah, Zhe, we can see your screen. Yeah, so you can get started maybe.
Hello, everyone. Welcome to my presentation, and thank you, Yingjie, for helping us to set up these slides. So my name is Zhe. I'm an assistant professor in the Department of Geography at Texas A&M University. And today my topic is CyberGIS-enabled decision support systems for disaster management. So before going to the detail of my presentation, I want to introduce our UCGIS CyberGIS and Decision Support System Research Initiative. So my group consists of 6 people from Texas A&M University, City University of New York, Arizona State University, and U.S. Geological Survey, and University of Iowa. So our research initiative aims to advance geospatial decision science using emerging technologies and transform the research outcome into high-performance geospatial-inspired software products. So today my presentation will be actually very much related with the work that we are doing in our research initiative, but I will give one detailed example of what about the CyberGIS decision support systems. And in the end, I will also introduce the summary of my future work. So nowadays, the world has grown more urban, more integrated, and with a greater of people at risk than before. So actually, we are facing many urban problems such as urbanization, disasters, and water and food shortages. So the urban area commonly contained with multiple administrative areas with conflicting social objectives often and uncertainty, which raises many hard decision problems in building urban resilience in disaster management. And my research is focused in developing an intelligent spatial decision support system and help cities to understand their vulnerability and prepare for the disasters. So before going to the detail of the application, I want to introduce some basic concepts. So what is actually the intelligent spatial decision support systems? So I see the intelligent spatial decision support system is a computer-based expert system which contains expert system or other intelligent components. So it actually combines conventional data or geospatial reference data and information and a decision logic as a tool for assisting a human decision maker. So these slides introduce a structure of expert system. As in the before I introduced what is spatial decision support. So it can be an expert system, but what is an expert system? So the knowledge, there are many important parts. First, I want to introduce the knowledge acquisition system. So that transfer the problem solving expertise from the expert to the computer program for constructing the knowledge base. And then the knowledge base contains relevant knowledge necessary for solving the problem. And the very important part here is highlighted in the red color is inference engine. That is acts at the brain of the expert system that provides methodology for reasoning about information in the knowledge base. But in the end, the knowledge is refined and updated for the future consolidation. So since the expert system is a computer-based system, so it requires the introduction of powerful computing system that had necessary speed, storage, and visualization capacity to process the queries on the large quantity of geospatial data involved. So therefore, in the next slide, I want to introduce the concept of CyberGIS. So I don't know how many of you are familiar with CyberGIS, but I think most of you must have heard about cyber infrastructure. So the cyber infrastructure consists of high-performance computing, advanced data storage, data repositories, and the visualization environment and people. And all those environments are aligned by the high-speed networks. And the CyberGIS is a geographical information science and systems that implement the advanced cyber infrastructure. So in this presentation, I formulated 3 research questions. So first, I want to know, how can expert knowledge be collected, represented, and transferred into a geospatial modeling process to support spatial decision-making? And how can spatial information uncertainty or vagueness be modeled in expert knowledge representation? And how can the intelligent spatial decision support systems integrate geospatial big data and generate intelligent human-machine paradigms? So I want to first introduce the case study. Is one paper that I published last year. Is a CyberGIS enabled multi-criteria spatial decision support systems, a case study on flood emergency management. As you know, in the case of different type of so in order to make the emergency management process efficient. So this work aimed to produce a platform for group decision making and collaborative problem solving. And here we use 2 decision models, weighted sum model and top system model, for addressing the problem that caused by the conflict objectives. And in this work, we have various data sources integrated into this computing platform, such as census data, Twitter data, and flood hazard map, and also a NOAA storm events database. So in this application, we want to know which area should rescue personnel go to first in order to save more lives. And in the second decision goal, we want to know which area had the most significant economic loss and need the greatest financial support to recover from the flooding events. So these slides introduce the general structure of the proposed decision support system. So the various type of geospatial data, as I introduced in the previous slides, like Twitter data, flooding map, and also census data, were integrated, actually were stored in the high-performance supercomputer called Roger. And here, the knowledge base was constructed based on the interaction between the user and the user interface. I will introduce this more in detail in the later slides. And as I mentioned, I have implemented 2 decision models, weighted sum model and top system model. So in the first step, we used the Twitter data. I think Yingjie has a very good introduction about how to work with the social media data. Maybe here I don't repeat that process, but in this application, the Twitter data was used as additional decision support tool for assisting the emergency management. So first we filter data with the different keywords, but unfortunately we did not find a good pattern. But later we used Twitter that with the ATX flooding tags, and then correlate that Twitter data with the number of flooding events. And we found a really good positive correlation between the flooding like tag tweets with the number of flooding events, meaning people more likely to tweet on that channel during the flooding events. And we are also able to integrate the Twitter into this computing platform, and people can zoom in, especially for the rescue personnel. They can zoom in to the map to observe what people are talking about, and maybe to go to help if they are experiencing the emergency. And before going to the detail of the decision-making models, I want to first introduce the general idea of multi-criteria decision-making, weighted sum model and top 6 model. So here is a very simple example that, for example, if you want to buy a car and you have 3 alternatives in mind, and you kind of evaluate each alternative based on different attribute values. So here you assign the weight for each attribute. Here is make, repair cost, price, and year of production, for example. And you as a decision maker, you might prefer a car that is cheaper than a good looking, for example. So in this case, you might assign the price at higher weight than other attributes. And the weighted sum model is one of the most often used model that to actually add, first multiply the value of each attribute value for each alternative times their corresponding weight and sum them together to produce the weighted sum. And that weighted sum value will be used as output as the total score for evaluating different alternatives. And the technique for order of preference by similarity to ideal solution top 6 model is another decision model, which is similar to the weighted sum. But the difference that instead of calculate the summed score, we calculate the distance to the positive and negative solutions, and then to compute the total score, as you can see from this formula. So these slides introduce the user interface of this computing platform. So in the left side, the user can assign the weight for different attributes by using this slider bar. Here we have a set of attributes, for example, total population of people over 75 years old and people without health insurance, etc. And then after user assign the weights, the user can select if they want to do this as a single user or a group of users. Meaning, if you are the only decision maker in this emergency situation, you might want to select single user. So the weight matrix will be automatically generated based on the sliding bar value. But if you want to work with the other decision makers, you might want to click on the group of users, and then everybody will submit the weight, and the weight matrix will be combined and then generalized into one weighting matrix based on a group of decision makers' submission results. And then user can also click submit WSM or submit top 6, meaning the user can select different decision models. After they have made all these selections, the map will be automatically generated. But of course, when user change the weight or change the methods, the map will be also updated according to the changes. So, and this slide shows the results. So as I mentioned, we have 2 decision goals, and the number in the left table represent the weight generated by decision maker. And then the right side illustrates the vulnerability value of the Austin City in the case of flooding. And you can see that for 2 decision objectives, the maps look similar. And for example, the area number 15, it has a very low vulnerability value in the case of disaster, because I think that is somehow near to the airport area. There was not so many people live there. So that's why it has a very low value. But for the weighted sum model, for example, for both objectives, the area number 4 and 7 and 8, they are very vulnerable. But for the top system model, only area number 4 and 5 seems be vulnerable. But area number 1, number 2 seems vulnerable for all the for both decision objectives and for both decision models. So we also conducted sensitivity analysis for this work. For example, we want to see how sensitive our results reflect to the change of attribute value. So for example, for the objective 1, the people without vehicle and number of children, those two attributes seems to very sensitive. For example, like if we make a small changes to the weight of these two attributes, the result can change actually quite much. That's the meaning of sensitivity analysis. And the challenging part of creating the decision-making model is how to validate our results. Of course, using the top sys model and the weighted sum model, we can generate the overall score. But how could we be sure that the result actually meet the decision maker's preference? So here we have conducted a questionnaire. So we randomly selected 10 regions with the same set of attributes, and we interviewed 6 decision makers, actually GIS experts, and let them to rank these 10 regions based on the attribute value that given to them. And then we compare the rank with our model's results to compute the error. For example, for both models, the objective number 1 actually produced the similar error results, and is much higher than the objective 2. So as a conclusion, and so multi-criteria decision making was used to combine different social vulnerability indicators to reach decision goals that are related to emergency management. And in general, weighted sum model produce more diverse values and a higher output category estimation than top sys model. But both models produce a higher error rate for the first decision objective and a lower error rate for the second. And this work also provides a fine-grained location information for rescue personnel to evacuate people who need help during disaster using Twitter data. But in the future, I think the text mining technique should be embedded to this tool to categorize the tweets to support different type of decision problems. And one limitation of this work that we have only involved a very few attributes, actually parameters here in the decision model. But in the future, we should actually look at more data sources and integrate more data or attributes to this decision platform. In the end, I want to also give a short summary of my future work and probably also to the future work that to our research initiative. So so far I have categorized my research agenda to 4 parts: population information modeling, critical infrastructure protection, urban security, and public health surveillance. So actually my work started with modeling population information in very early time, since population information is so important in emergency management. All the services, all the critical infrastructure, they were built to serve people. And without knowing where are the people, actually it's really hard to to do any emergency services. So first I developed this in the left side picture, a spatial temporal population model to estimate how many people are inside the risk area at a certain time. And later in year 2014, I have developed a fuzzy multiple attribute decision-making modeling for vulnerability analysis on the basis of population information for disaster management. For that application, is similar actually to the application that I have just introduced. But the difference is that here I use the fuzzy modeling, and here I focused in the social vulnerability, such as I want to find out where the hotspot has most of children and people live in, so the rescue personnel can go there to rescue more, for example, more children. And later, I also got interested in the critical infrastructure modeling. For instance, in year 2018, I developed this spatial fuzzy influence diagram to model spatial object interdependencies. So you know, in the world, all the spatial objects, they are interdependent to each other. For example, if you consider a power line as one spatial object, a fail of a power line might also cause a fail of telecommunication networks. So in this case, how do we model these complex interdependencies? And this was published in year 2018 to the International Journal of Geographical Information Science. So I have applied this spatial fuzzy influence diagram to model the tree-related outages. So here, the red point represents the vulnerable locations that in the case of a winter storm, which tree gonna cut the power line. And later, last year, I had two papers for urban security applications. So the U.S. government, they have noticed the nuclear waste has been stolen to build a nuclear weapon. So we have developed intelligent sensor network. In the left picture, you can see this is sensor network, and this is the phone app we have developed in our mobile phone. So the volunteer carry this sensor, walk around the campus, and that will record the radiation level at your current location that will transfer to the Amazon cloud through this mobile app. So this data update every second, meaning we form a really large spatial temporal geospatial data cloud. But the goal is to detect anomalous radiation source, meaning where is a nuclear bomb, for example. But it's really challenging since the data is so huge and we need intelligent algorithm to detect anomalous locations. So for this application, I have developed two apps. One is using voice and creaking and the sensor networks to detect. We did 10 different type of experiments, and our accuracy has reached more than 90%. If you are interested, you are welcome to look at our article published in year 2019. And for the second app, we use the KNN algorithm to detect anomalous radiation source, and that work has been published in the cartography and geographic information science also last year. For the public health surveillance, I have organized a working group in the convergence program that was funded by NSF. So the goal of this work is to observe the spatial pattern of COVID-19 mortality rate with various social, demographic, and spatial variables, such as social vulnerability and urbanization rate and healthcare accessibility and living habits. So we are still working on this project. Hopefully we will come out some good stuff from this. And education, I believe education and research, they are always connected to each other. I'm also organizing a K-12 Geography and GIS Science education program at the College of Geosciences and that Texas A&M University, and that was funded by Texas Department of State Health Services. So the kids has made 2 posters. They have submitted a poster for modeling the Houston's air pollution for the 2020 AG annual meeting. And they have also submitted another poster on the topic of urban social vulnerability assessment and the COVID-19 and natural hazard to our UCGIS symposium. So in this poster, they want to investigate the vulnerable locations in Houston area in the case of COVID-19 and hurricane. So because we live in Texas, the hurricane season is coming soon. We want to know how people react with the double threat. And you are welcome to visit our poster. And thank you very much. So do you have any comments and questions?
So thank you very much, Jo. Thank you very much, Jo. So maybe because of the time, maybe we can first switch to our next presenter, Lei. And meanwhile, if the audience has any question, you can answer them just using the voice. Is that okay?
Yes, yes. Thank you.
Okay, great. Thank you. So you can check the question tab to see any question.
Hello, everyone. Can you hear me?
Yes.
All right. Thank you very much for the opportunity to introduce our research on the changing roles of social media in disaster resilience. And I think this is very closely related to the first 2 presentations, Ingrid's presentation and Jo's presentation, which are both focusing on how can we use or leverage in different social media platforms, as well as different CyberJS applications to improve our disaster resilience. My name is Lei Zhou, and currently I'm an assistant professor in the Department of Geography at Texas A&M University. I'm very happy to have this opportunity to introduce, even though we were supposed to be in Hawaii, but because of COVID-19, the only way we can meet is online. But don't worry, because next year we're going to meet in Philadelphia. And I put one picture of the Honolulu in my first page so that you can feel a little bit about the relaxing environment in Hawaii. So the reason why we care so much about disaster events is because it has caused too many damages to our human communities. So in 2018, on records, there are about 800 disaster events causing 178 billion economic losses with 12,000 fatalities around the world. So this is a very pressing and very important challenging for almost every human community in the world. Is how can we improve disaster management? How can we reduce the economic loss as well as reducing the human impacts in terms of the fatality and injuries? To think about how we respond and recover from disasters. This is the 4 phases of emergency management cycle defined by the FEMA in the United States. It involves 4 steps in here. The first one is the preparedness. So preparedness defines all activities and behaviors before a hazard happens, including the emergency planning, training, exercises, and how people to predict early warning the disasters. The second phase is the response, which were during the disasters. A lot of activities such as life-saving, evacuation, stabilization, as well as property preservation are all considered as response behaviors during a disaster. The third phase is the recovery, which defines as the short-term behaviors and activities to help community return to a normal state. And finally, between the 2 disaster cycles, there are a lot of activities that can educate people to better prepare for the next event, assess the potential damages, and help infrastructures and communities to improve the local resilience and reduce the potential damages. Those behaviors could be conceptualized as mitigation. So these 4 phases of emergency management have been applied in disaster management for many years, but there's one challenge haven't been solved for a long time, which is there's no timely data to describe human behaviors to monitor the emergency needs in different communities before, during, and after disasters in a short time period. So that's a challenging here, and that's the reason why social media have been frequently introduced for studying disaster management during the past at least 10 years. So why social media can provide so many information that are timely and not provided in traditional databases? That is because social media actually provides 4 dimensions of information, including the spatial, temporal, network, and content. And by analyzing one or several dimensions of social media data, we can actually using or leveraging this platform and data to help communities to have better early warning platforms to monitor the crisis and the emergency needs in different communities, and also to monitor the mobilities, which could be considered as the evacuation and recovery before and after major disaster events. But social media used in disaster management is actually beyond the 4 dimensions in here or the previous applications. Just like Indra mentioned in his presentation, Hurricane Harvey actually was named or kind of like be considered as the US's first social media storm. So this is the first time there are so many people started to use social media as a way to request rescues. So it's very different from previous events, because in previous events, people have started to use social media to request for help sometimes, but not as frequent as we see in Hurricane Harvey. So stem from this idea, I have been working on this NSF Rapid project, which is called The Changing Roles of Social Media in Disaster Resilience, leading by my PhD advisor, Dr. Nila Lam in Louisiana State University during the past 2 years. In this project, we propose that the way people using social media or the roles of social media in disaster management has changed a little bit, slightly in the past few years. So the very first beginning stage, when every social media platform or social network platform is developed and become popular, it is a platform for people to network. So during disasters, people will share and discuss disaster information, mostly with their families and friends. And later on, social media become a medium platform. So this is a place where people can publicly updating or commenting on disaster impacts. So it's kind of like people are talking about what is happening right now. Now, later on in Hurricane Harvey and after Hurricane Harvey, people started to use social media as a tool that can build more strong communications even between strangers, because this is a tool that can help fast responding and also can support the rescue missions during emergencies. So in this project, my work and our group work is mainly about the 4 parts, 4 objectives here. The first one is a framework. We need to develop a framework that can help us to measure social media uses in disaster management so that we can compare the spatial and temporal patterns. The second objective is about the patterns. We need to validate, we need to test if the framework, the indexes we created in the framework is valid and useful to compare and measure the spatial temporal patterns of the social media uses in different events, in different locations. The third objective is about the changing roles, which is the main objective of today's talk. It's how users request rescue on social media, and subsequently, can we really use social media as a reliable platform for future events? If it's not, it's a good platform, how can we improve the efficiency? Now, lastly, it's how to improve disaster rescue using social media in future events, not only for the rescue missions, but also for other mitigation and preparedness for future events. So here's the outline. First, we'll introduce the data and the methods, and then second, we'll use the data and the methods to apply them to Hurricane Harvey and show the patterns of the disaster related to the uses in different stages of the emergency management. And third part, we'll talk about the new use of social media in disaster rescue. And finally, we'll give a summary about the lessons we learned from Hurricane Harvey. So Hurricane Harvey is not the only data we're going to look at today, because we are going to investigate the changing roles of social media. So we have to have a baseline, which is a reference, compared with Hurricane Harvey. So we choose Hurricane Sandy as a reference to compare how people use social media differently back in 2012 and then in 2017. Those 2 hurricanes could be considered as most destructive and costliest hurricane events in US history. And in both events, social media have been widely used, so give us a lot of data sources to analyze. And they happen in different places and in different times, so that we can also compare the spatial temporal disparities. So just give you some information about the data we collected in here. For Hurricane Sandy, we actually get like 16 million tweets in about 1 month. And for Hurricane Harvey, also for 1 month, we collected about 45 million tweets. And if you look at the damage, both hurricanes actually caused almost considerable damage to the coastal communities in New York and in Texas. So this is a framework we developed, which we called the Twitter data visualization and mining framework. In this framework, we have 3 steps. The first one is the data collection. We're trying to collect data in 2 different databases. The first one is the random collection. We collect the background tweets, which indicate the general uses of social media in different locations at different times, so that this dataset can be used as a reference to normalize the disparities of the user conversation and social media activities in different places. And the second is a keyword and rule-based collection. We're trying to collect the tweets related to Hurricane Sandy and Hurricane Harvey or any other events. So those tweets are the target tweets we're going to analyze and we're going to extract the useful information from. The second step is data processing. So in data processing, a very important step is geocoding, because only 1% of the tweets have geotext. And as Angel mentioned, since 2019, I think it's November or October, Twitter has deactivated the function of attaching accurate geotext to tweets. So it turns out we need some functionalities to extract location information, not only from the geotext, but also from the tweet contents, as well as the user profiles. So we developed a geocoding module using OpenStreetMap and sometimes using Google Geocoding API in a local server, so that we can extract location information of each tweet from different sources. And the second part of the data processing is the content analysis. So we not only want to know when and where people talk about hurricanes, we also want to know what people are talking about hurricanes. So in this analysis, we will introduce the sentiment analysis results. And both the spatial and the sentiment information could be aggregated in different spatial and temporal scales, and those scales could be translated into Twitter indexes. So let me show you some results about how these indexes work in different events and different locations. So the first Twitter use pattern in here is the temporal patterns in the United States. So blue lines in 2 figures, Hurricane Harvey on the left and Hurricane Sandy on the right, indicate the normalized discussion intensity of the specific event. So you can see usually people talk about hurricane events after hurricane makes its landfall and in the subsequent few days when the hurricane events causing real damages. And the red lines in both figures indicate the public sentiment or the emotion towards different events. So the sentiment ranges from -1 to 1, meaning negative sentiment, meaning people are kind of like depressed about the disaster. And the positive usually are people who are brave for people who suffer from disaster, or maybe reporting that they're happily not affected by disasters. So we can see that the way people using social media spatial temporally is a little bit different. So in Hurricane Sandy back in 2012, the highest discussion intensity were observed right after the landfall of Hurricane Sandy. But for Hurricane Harvey, it's a little bit different. So the highest discussion intensity were observed a few days after the first landfall of Hurricane Harvey. That was because after Hurricane Harvey made its landfall, people or citizens in Houston, they experienced unexpected rainfall. So they're unprepared for Hurricane Harvey. At the very beginning, they did not think Hurricane Harvey would cause so much damage to their communities. But after they received a lot of rainfall and flooding events, they were trapped in their homes. They started to use social media to acquire information, as well as maybe requesting rescue in our further analysis. So that's one difference we're observing here. The second difference is about the public sentiment. So in Hurricane Sandy, the public sentiment were lowest during the landfall. But for Hurricane Harvey, it's a little bit different. It was in the recovery phase. And that was because Hurricane Harvey was a unique case. While Hurricane Harvey was still moving towards Louisiana there was another hurricane called Hurricane Irma formed and made a landfall in Florida. So it turns out people can easily connect the two events together and show more negative emotions on social media platforms. And if we aggregate the data by county level and visualize the county level racial indexes for two different events, we can observe similar patterns in here. So most of the counties in red, which means their public discussion intensity are higher than the national average. They're concentrated in the affected regions and closer to the hurricane track. So most of the discussion were generated in affected areas that provide us a lot of abundant information to analyze. So if we zoom in into the affected region of Hurricane Harvey, we can aggregate the data by different time period and define it as the preparedness, response, and recovery, so that we can observe how public responses to this event change through time and space. The next question we're trying to investigate is what makes the public responses or perceptions of the disaster differently in different locations and different emergency phases. So that's the reason why we run the stepwise regression models between the racial indexes we developed in different phases of the emergency management, as well as the 17 geographical and social variables, which were selected and believed to be highly correlated with the concept of disaster resilience from previous literatures. So two important factors, geographic factors we considered in here are the flood threat and the wind threat. So Hurricane Harvey is very unique because if you look at the two maps in here, the threat levels from flood and wind are quite different. So usually the spatial patterns of the flood threat and the wind threat are very similar for hurricane events, but for Hurricane Harvey, it actually shows quite different events. And that difference is also observed from the regression analysis results. So usually at the very beginning in the preparedness phase, the wind threat is more significant in motivating people to tracking the hurricane information on social media, because people feel on the risk based on the prediction of the hurricane track. But later on in the response phase, people started to notice that hurricane track is not the only threat they will suffer from disaster. Rainfall threat is another type of threat that they may suffer from Hurricane Harvey. So it turns out in the response phase, rainfall threat is more significant compared to the wind threat. The second phenomenon we've observed in here is that communities with better socioeconomic conditions usually had higher disaster-related Twitter use in all three phases of the emergency management during Hurricane Harvey. And this result is consistent with the studies of Hurricane Sandy, meaning that this is a new type of digital divide. Traditionally, when we think about digital divide, it's about the accessibility to digital resources for different communities. Like rural communities may have limited accessibility to digital resources. But nowadays, the problem is they not only have limited access to digital resources, but also they have limited knowledge about how to use the digital resources to acquire information during emergencies or during disasters. So that's another thing we should pay attention to. Now back to our previous proposed idea about the changing roles of social media in here. We have tried to visualize the spatial temporal patterns of social media use as people publicly discussing disasters, which means social media used as a medium. And slightly different between two different events, but we can still see the general patterns are very similar between Hurricane Sandy and Hurricane Harvey. So now let's move to the third functionality of social media, which is serving as a tool for fast responding and assisting the rescue missions. So there are in general three questions we're trying to answer. The first one is, did more hazard victims request rescue online? Second one is, how effective was Twitter use in emergency rescue? And third one is, can we improve the online rescue process for future events? So to answer the first question, we did a text mining for the Twitter database we collected for Sandy and Harvey. So for Sandy, in the 16 million tweets, only about 4,000 tweets mentioned the word rescue. And that number has increased dramatically in Hurricane Harvey, even though the number of Hurricane Harvey related tweets are 3 times of the Sandy related tweets. The number of tweets mentioning the word rescue is about 1 million. So the bar of size of the bar indicated the percentage of the tweets in two different databases. But if you look at the absolute number of the two events, you can actually see more significant disparities in two different events. And the same for the word help, SOS, and the twist containing addresses information. Those 4 keywords and address information are considered as twist, potentially indicating people may need help. We also did a text mining of the collection of sample tweets which request rescue online, and trying to evaluate how people request rescue online based on the tweet content themselves. So first knowledge we discovered is that the top 3 keywords of the tweets request and rescue are Harvey SOS, Harvey Rescue, and the Cajun Navy. So all 3 keywords are related to non-governmental organizations. In other words, non-governmental organizations play a more significant role in the online rescue process compared to telephone or a traditional rescue process. And if you're not familiar with Cajun Navy is actually a voluntary organization which was formed in 2016 during Louisiana flood. And nowadays, all the people who are volunteered in coastal disaster rescue missions, they usually call themselves Cajun Navy along the Gulf of Mexico, and sometimes maybe not even along the Gulf of Mexico, but along all the coastline in the United States. We can also investigate what kind of information were provided in those rescue requesting tweets. So most of them do provide address information, but very few of them provide like how can the first responders contact them, how many victims needed to be rescued, what was the flood condition, and the reason why they use Twitter instead of other traditional methods for rescue requesting. So this kind of information can help us and also help the citizens to understand if they need to request rescue, what kind of information they should provide so that they can help the first responders to better organize or schedule the rescue activities. Now, to understand how effective was Twitter use in emergency rescue, which is hardly to obtain from the Twitter text mining, so we conducted a survey with 34 questions to people who request rescue online using Twitter in Houston and the surrounding urban areas. So there are about 2,000 people attempted to enter the survey through the online platform Qualtrics. But at the end, only 195 people meet the criteria to enter the survey and finish the survey results. So let's have a look at how people feel about the effectiveness of Twitter use in emergency rescue. So the first question we ask is, why do you use social media to ask for rescue? Normally we would think, well, if you need rescue, you probably would call 911 or call your relatives or friends. So usually people will think, well, Twitter or social media are very easy to use. And they think, half of them think, social media can directly help them reach the first responders. And some of them mention that they tried all methods possible to request rescue. And about 1/3 of them experienced telephone signal unstable situations, or they mentioned that 911 was failed to connect during Hurricane Harvey. And the second question we ask is, who rescued you? So which organization or which method actually works? So it turns out more than half of the people were rescued by the relatives and the friends. And then 40% were rescued, mentioned that volunteers provide assistance to rescue them. And then police department, Coast Guard, and Texas Task Force were also mentioned as the people who rescued them in this question here. So what we can see is another validation of our previous conclusion, which means non-government organizations plays a more significant role in the online rescue process. The third question is very important about saving people's life. Is about how long did it take for the rescue? So it turns out most of the rescue took about 2 to 5 hours, so 41% in here. And the one thing we also need to notice is that about 10% of the people mentioned that it took more than 10 hours to be rescued. And sometimes more than 10 hours it might be put the victims into dangerous situations. So that's something we also need to improve in the future disaster management and rescue missions. Now, the last question is, in general, how do people feel the usefulness of Twitter for seeking help? And most of them feel like Twitter are very useful and extremely useful, but they also pose some challenges in here. So let's go into the next slide to see how useful based on the survey results and what kind of implications we can derive from the survey. So we also evaluate the effectiveness of Twitter use for disaster rescue. We're trying to compare the different methods of response rate and the assistance provided rate. So if you look at the first two rows in here, calling relatives or friends or calling voluntary organizations are the most responsive and most helpful platforms or methods to receive rescue assistance during emergencies. And Twitter, in our survey here, in these 200 cases, actually performed better than calling 911. So very interesting thing you can see is that because our survey responders, they all use Twitter, but only 42 of them attempted to call 911 during Hurricane Harvey. And the people who request help on Twitter, 70% of them received a response, and 43 of them receive assistance. But for people who use 911 to request rescue, only 59 of them received a response, and only 38 of them received assistance during Hurricane Harvey. So that's something we discovered in here is that maybe in the future we should find a way to combine traditional rescue process with the online rescue process so that they can supplementary each other and provide a more reliable rescue requesting platform in the future. Now, let's look at how we can build a connection between the victims and the first responders. Because if you notice in the previous slides, there's a gap. People requesting for rescue online, but how did the first responders receive those information? So this is one of the platforms established during Hurricane Harvey, and this one called crowdsource rescue. And this one is very successful by inviting a lot of volunteers to crowdsource rescue requests from social media, and then send those information to nearby registered volunteers and first responders who have the resources to help the flood victims. So based on the website, this website application are being applied in 23 incidences and helped more than 50,000 people, survivors helped. So that's an impressive achievement. But after Hurricane Harvey, we actually contacted the founder of this crowdsource rescue, and what he told us is that they actually manually collect rescue requests through volunteers. So that caused a lot of issues in here. For example, maybe 2 volunteers may collect duplicated information and input duplicated information in the online rescue platforms. The second is that it requires many volunteers to keep monitoring the disaster and the rescue request on social media. So which is also a huge challenging for this company. So to help them automatically accomplish the process of identifying tweets request and rescue, extract the location information, and send the location information to the nearest first responder, we developed a similar tool called a victim locator, trying to first classify if one tweet is requesting for rescue through a deep neural network. And the second step is we use a rule-based geoinformation retrieval geoparser to extract the location in text messages from the tweet messages. And finally, we use Google API to convert the address information into coordinates, so those coordinates could be labeled on a map and be visualized by the first responders. And as you can see, most of the rescue requests in here, because we only use the detailed address information in the first attempt analysis in here. So only 824 tweets were successfully located. But most of the tweets who requested rescue were generated in the August 27th and 28th, which were during the time period when the highest discussion intensity were observed on social media. If you can recall from the first temporal trend of the social media discussion in US in Hurricane Harvey. We also show the dynamics of the locations from the August 27th to August 31st to see how where are the people requesting rescue in different dates during Hurricane Harvey in here. So now let me give a brief summary of what we have accomplished in here. So first finding we found is that digital divide still exists in terms of social media use. Community with better socioeconomic characteristics had higher disaster-related Twitter use during Hurricane Harvey. And the second finding is that social media can be used for emergency rescue and worked pretty well, depending on based on the survey results. More people resorted to social media to request rescue during disasters, and actually non-government organizations are playing significant roles in emergency rescue. Now, the last finding here is about the victim locator. We're still refining the results, but I think the developed tool could successfully identify rescue requesting tweets and locate the victims from tweets having detailed address information. But there are also some challenges we should never ignore in addressing social media for emergency rescue. For example, the inconsistent online rescue requesting approaches. As we can see from the text mining results, different people are using social media differently when they request rescue. They provide different information and they probably use different hashtags. So in future events, if we really want to make it into a practical tool, we need to make sure people are aware of the hashtags and the accounts or contact information if they need requesting rescue online. The second is lacking updates on the rescue requesting processes. So if one people was rescued, but he or she did not delete the post about the requesting rescue tweets on social media platforms, it turns out this information will be repeatedly collected by volunteers, and then more and more volunteers will be sent into the same location to check if the person is rescued or not. So currently, there is very few information about the updates of the rescue request in progress. The third thing we also need to pay attention to is about the biased social media user composition. So if we look at the people who request rescue online, it is almost the same pattern as the people who use social media during disasters. So those are the communities with better socioeconomic characteristics. But how about the communities in rural areas? They have limited access to resources and they have limited access to the information. We also need to pay attention to those communities as well. The last question is about the privacy issues. So when people post the location information on the public social media platforms, they actually provide the home address in there. And after disaster, how can we organize the information we collected and protect the privacy of the users who used to request rescue online? So that's something I also need to address in the future. But even though there are some challenges, I think we're still in the best time to use different platforms to build different applications and to improve emergency management so that we can build a better future in a sustainable future. So that's all my presentation. If you're interested in any of the data or the papers in here, you can go to our project website. We have some sample data and the link to the papers in there. And any questions are extremely welcome. Thank you very much.
Okay, thank you very much, Chen. Thank you very much, Lei. Sorry. So because of the time issue, let's switch to Chen. And meanwhile, if you have any question for Lei, please feel free to use the question function, and Lei, you can directly answer the question of the audience in the question function. So now I'm making Chen as the next presenter. So our session is expected to finish at 2:30. So if you have other schedule conflicts, please feel free to leave. But if you can, please stay for our presentation from Chen. Thank you.
Okay. So hello, everyone. My name is Chen Xu. I'm an assistant professor in Wyoming Geography Information Science Center at University of Wyoming. So we have seen GIS technologies are applied to different aspects of different areas of society in our previous three presenters, and I think it leads well to this presentation, which I'm going to introduce to you this initiative on convergence of GIS science, humanities, and social sciences. And my goal today is to introduce to you this survey that is about to be conducted to UCGIS community in the near future. So let me first introduce our working group. So this group is led by Dr. Suren Shaw, and I'm the co-leader. And we have 8 members from different universities. So working with, so our current project is focused on design and conduct this survey, which I'm going to introduce to you today. But here I want to give you some background contextual information about this initiative. So basically is what we see in GIS, GIS technologies and GIS science. In a way, it's a reduction technology. So it traditionally rooted on concept of absolute space, Cartesian coordinates, Euclidean geometries, and also employ quantitative methods. But at the same time, we see that there are entities that cannot be easily reduced. For example, for place, we can talk about place as a location or as a socioeconomic status. But at the same time, there is a people's sense about place, which is not easily, which cannot be easily be reduced. Or when we reduce this place to just a location or to the social economic status, then we lost useful information. So in humanities or social science, it tends to they tend to be concerned more about a place or people's sense about place or the histories about place. And in this way, it privileges the use of qualitative methods and techniques. So we see here is an epistemological dilemma where GIS science in general advantages reductionism, but humanities prefer holism. So especially when today we are seeing more and more information technologies is applied to different area, for just like we already seen in the previous three presenters. In social science and largely in humanities, there are researchers talking about the need to rethink the question of technology and its relationship to society and culture. So this discussion or this looking at this present trend is remind me my days in university when I studied engineering cybernetics, where at that time our focus is more on how do we automate, for example, manufacturing lines. And at that time, although the concept of applying AI or other cybernetics theories to help decision making about societies, but there are insurmountable difficulties that actually the concept didn't fly. But now we see this trend of, and we also see the technology is really it's possible that we better use we could use information technology to better serve the society, but at the same time we could ask how could we better serve society with information technologies, especially when our target is about people. How could we better serve society with information, how society with these new technologies, new concepts, new methods. So this leads actually to Drs. Alberto Giordano, Dr. Stern Shaw, and Dr. Diana Stanton in UCGIS Symposium 2019 last year, organized two panel sections on geospatial humanities and proposed GIS science and humanities study. So in last year's symposium, questions being discussed in the panel discussions include, for example, what will it take for this collaboration to be truly transdisciplinary research effort, and what could be benefits of such collaboration to humanities and to GIS sciences, or what would a curriculum in geospatial humanities look like at the undergraduate and graduate level. So after last year's symposium, the group planned to conduct a survey of the UCGIS community to collect input and then conduct another survey of broader digital geospatial humanities and the humanities at large and the computational social sciences communities to collect input. So the goal is to understanding to collect input from the community to help us better making progress with this initiative effort. So here is, before we go into talk about the survey design, I want to quickly preview, provide you with an overview about overlay this progress. So we added, at this stage, we added social sciences into this initiative. So largely is because there are a lot of discussions, or there are a lot of theories or methods that we could leverage from social sciences interaction with cybernetics, with technology. So we want to bring in those useful those resources to help us to broaden the scope. So that is where we see this title of this initiative is a convergence of GI science, humanities, and social science. Then we designed and developed this survey questionnaire, which I'm going to present to you next. We have received an IRB approval from the University of Southern California with the assistance from Dr. Jennifer Bernstein. She is the UCGIS Communications Committee Chair. Then Diana Sinton helped us put the survey on SurveyMonkey. So we are going to conduct this survey through SurveyMonkey, and currently we put the survey on SurveyMonkey for the UCGIS board members to review and comment. And we did receive the feedbacks from the board members, and we have completed the revision of this survey questionnaire. So let me present to you this survey design. So the survey basically has 3 parts. First, we want to collect basic information, and then there are 3 key questions, and there are several optional questions, survey questions. So totally there are 13 questions, including multiple choice questions and short answer questions. So here is the questions that we asked in this survey questionnaire. So these 6 are the basic information questions that we want to collect from our surveyor. So what is so basically this question about the professional position and where they are employed, and their research area, research topic, and research method. And then the 6th one is we want to gauge the interest or the people's response to whether they are interested in this concept of GI science, collaborate or develop synthetic collaboration with researchers in humanities and social sciences. So then if people are interested or are in support this collaborative research effort, then we would ask them to answer these key questions about, from your domain perspective, what would be the 3 major advancements in your field that benefit the most from a synthetic collaboration with other domains. So these are the domains that we talked about are the 3 domains, humanities, social sciences, and GI science. So then after that, then we want to ask about basically about people's people's input about what are the main challenges in developing convergence research across these 3 domains. So then the last question, the key question that we want to ask is about, in order to more effectively teach convergence research, then in higher education curriculum, how should we, or what kind of changes could be made to the curriculum in order to facilitate, to really teach effectively this convergence research? So these are the 3 key questions that we asked in this survey. Then there are 4 optional questions. These are questions where we ask that if people are really their extra time, effort, and want to contribute more to this survey, then they could answer these optional questions. So there's, for example, as people in, for example, in GI science, what's their perception about, for example, about humanities or social sciences, what's their perception about. So the goal is basically to, for example, exactly where Hans van Forster say here, it's the interaction becomes communicative if and only if each of the two see himself through the eyes of the others. So we want to see whether hopefully we get some interesting input from this question. And then we have this methodology questions about method. So for example, how and why not can your domain benefit research in the other domain concerned by the survey? Or do you think the concept, place, or time, can be helpful? And then a current GIS science visualization approach sufficient to support research needs in humanities and social sciences. So basically, we hope that if people provide us answers to these optional questions, then it could help us individually in different areas using different methods to help us to think largely about how could we from each different area domains, how could they contribute to this effort. So these are the design of the questionnaire. So the next step is the survey is currently on hold due to the COVID-19 pandemic, but we plan to conduct the survey of the UCGIS community soon. And after that, then we are going to expand this survey to larger communities. So this that is all from my presentation. Thank you for your listening.
Okay, thank you very much, Chen. And thank you for all the audience that has stayed with us. Apparently, we have many exciting research to share with you. So, Dr. Shilun Xiao, do you have anything to say as a last statement for us?
Okay, thank you, Yingjie, and thanks to all of the presenters. So UCGIS Research Committee has these 3 research initiatives ongoing. You are welcome to visit the UCGIS website and read more about them and join us on these efforts. Since we are running over time and we have another GIS science and COVID-19 panel session starting very soon. So I think we will end this session right here. Thank you all for your participation. Thank you. Bye-bye.
Thank you.
Thank you, everyone. Our next session will be at 3. Join us.
Thank you.
Thank you.